talk about mental math. When it comes to addition, the easiest problems to do in your head are the ones where you don't have to do any sort of carrying. So with 115 plus 234, I can just add the ones digit, adds the tens digit, and add the hundreds digit, and nothing carries over. I just add all the digits up from left to right, and I get 349. Even though these are pretty big numbers, it's pretty easy to do in your head, whereas something like 97 plus 58 is a little bit harder to do in your head, because if you were to do the same thing, well, the 9 and the 5, those are going to carry over. I mean, sure, that's going to be 14, but the 7 and the 8, those are going to carry over. You're going to have 15 there. You're going to have to add 1 to the 10th digit or whatever, so it's a little bit harder to do in your head. You can still do it pretty easily, but what are some strategies to do a problem like this? Well, similar to how we talked about in the previous section, you could split this 55 up as split the 58 into 3 and 55, and then just borrow the 3 from the 58, combine it with the 97, and then be left with 100 plus another 55 left over, and so you get 155. And so even though I'm writing this out to sort of show you my thought process, this way of thinking makes this problem a lot easier to do in your head. 513 plus 890, you could apply that same concept, just borrowing in a different way. So instead of borrowing like 3, you could borrow like 10 from like the 513. So you're left with like 503 over here, and then you would make the clean 900 over here. So this is really 503 plus 10 plus 890, right? And so so this would be 1403, right? 500 plus 900 is 1400, 1403. Something like this, let's say you're like out shopping and you see 3 items for $24.99, $74.99, and $14.99. How much does that all add up to? Here's where like kind of rounding and compensating is really useful. So this is basically 25 plus 75 plus 15. 25 and 75 makes 100. So this is basically 115. But when we round it up by a total of 3 cents. So we have to subtract to compensate for that. So this is 114.97. Let's do some strategies for subtracting. 453 minus 122, something like this. There's no carrying, so you can just subtract left to right, similar to before. So this would be 331. But 212 minus 37, you have to do some carrying if you were to do that sort of process, so that's not going to work as easily. One way you could think of this is, so 212, you could subtract 12 first to get to 200, and then 37 is like 12 plus 25, so subtract 12 first and then subtract the remaining 25. You would end up at 175. One way that you could think of like what's going on here, so here's 37. Let me actually move that a little bit to the right. Here's 37. Here is 212. And so this distance between these two numbers, the distance is 212 minus 37. That's like kind of what subtraction is. Subtraction is like a distance between two numbers. And now if we were to like shift over by 12, like subtract by 12, so 25 and 200 here. So move both of these left by 12. The distance between those two numbers is going to stay the same because we're really just like kind of taking this and moving that over 12 units. So if we subtract 12 from both of these, then that difference is going to stay the same. So this distance is really the same distance as 200 and minus 25. Okay. We can apply that same concept to this problem right here, 62 minus 28, except instead of subtracting from both of them, you could add to both of them. So here's 28, here is 62. I don't want to subtract 28, that sounds annoying. I could subtract 8 first and then subtract 20, but I don't want to subtract 8 from 62 in my head. That's like mentally slightly more taxing than the alternative, which would be to add 2 to both of those so that I can subtract 30, because subtracting 30 is really easy to do in your head compared to subtracting 8 followed by subtracting 20. So this is the same as just adding 2 to both of those. So 64 minus 30, that's really easy to do in my head. That's just going to be 34. Okay. Multiplication, there are a lot of ways that you could multiply things in your head. So 14 times 8, for example, you could think of this as 14 times 2 times 2 times 2. So just like double it a bunch of times. So 14 times 2 is 28, then 56, then 112. So this would be 112. You could think of it as like, this is 10 times 8 plus 4 times 8. Because you have 14 groups of 8, so that's 10 groups of 8 plus 4 groups of 8. This is like a distributive property thing going on here. So this is 80 plus 32, which makes up 112. You can think of it that way. 23 times 12, you could do like that same sort of thing. This problem's slightly more complicated though, but 23 times 10 is 230, and then 23 times 2 is 46. Add those together and you're going to get 276. Okay, so thinking of that using the distributive property will sort of make your life a little bit easier there too. Multiplying by 5 is special because 5 is the same as like 10 divided by 2. So what I usually do in my head is divide whatever that number is by 2 first, and then multiply by 10 by just moving the decimal over or just adding a 0 at the end. Okay, so 512 divided by 2, that's pretty easy to do in my head. That's 256. Then I multiply that by 10, and that's equal to 2,560. Multiplying by 90 or 9 or 999, like anything like that, that's pretty easy to do in your head as well, because what you can do is say, well, 99, for example, is the same as 100 minus 1. And then just do like a distributive property thing here. So 80 times 99 is the same as 80 times 100 minus 80 times 1. And so this is equal to 8,000 minus 80, which would be 7,920. Okay. And here's one that is definitely not covered in the book, but I learned this one a long time ago, and this is one of my favorite tricks to actually multiply numbers in my head. And it's actually like somewhat useful. So 16 times 18, anytime that you have numbers that are like 2 apart or really an even number apart. So the catch with this is you kind of have to know your perfect squares. If you don't know your perfect squares, like if you don't know what 17 squared is, or for example, then like you're not going to know how to do this, or you're not going to be able to do this and won't be useful anymore. But let's assume that you know your perfect squares. What you could do is recognize that 16 is the same as 17 minus 1. And then 18 is 17 plus 1. And if you were to FOIL this whole thing out, this would end up equaling 17 squared minus 1 squared, which is just 1. So if you know your perfect squares, if you know that 17 squared is 289, then this is just equal to 289 minus 1, so 288. And you could do the same thing for like 14 times 16. this is going to end up being, for the same exact reasons, 15 squared minus 1, so that's going to be 225 minus 1. You could even do, like, let's say that I wanted to do 15 times 19. I could do this one similarly. These are an even number apart. So this is 17 minus 2 times 17 plus 2. And so if you FOIL this out, you get 17 squared minus 4, or minus 2 squared. And so this is 289 minus 4, which would be 285. If you want to do 21 times 19, this one's really easy to do, because this would be 20 squared minus 1, so that would be 400 minus 1, or 399. If you could do 79 times 81 in your head, this would be, because that would be like 80 squared minus 1, so that would be 6400 minus 1, so 6399, etc. So I actually really like that trick, so I thought I would tell you. It's not in the book, though. Anyway, estimation. So let's say that we just kind of want to estimate some sums. The whole idea behind estimation is the bigger the place value, the more relevant it is to the sum. So the hundreds place is really relevant. You can kind of just ignore the ones place when you're adding these really big numbers, right? So this is basically 500 plus 600, right? So you could just give a rough estimate. This is basically like 1100. It's not very accurate, but like it's a good kind of, and it's like an underestimate too, right? Because you're like getting rid of this whole thing and getting rid of this whole thing. If you wanted to be more accurate, you could say, well, this and this are like, if you combine them together, that's pretty close to 100. So it's not quite like 500 plus 600. There's like an extra 100 going on there. And it's actually going to be a little bit less than 100. So this would be pretty close to 1200, and really it would be like a little bit below that. Okay. You could totally just overestimate both of these numbers and say, well, an overestimate for this sum would be like 600 plus 700, which would be 1300. That would be like a really big overestimate, but you could do it. And you could also just round each of these to the nearest 100. So this kind of rounds up to 600. This rounds down to 600. So in total, pretty close to 1200. You could do a similar thing with bigger numbers. This is like 4,000 plus 9, basically 4,000 plus 9,000. So this is like pretty close to 13,000. And you could like get more accurate by like paying attention to the hundreds place as well. You could say that this is pretty close to like 13,700-ish, or whatever. You can get as like accurate as you kind of are able to do in your head. 814 minus 565, you can kind of just round both of them. So this is pretty close to like 800 minus like, you could even round that to like 550 if you want, and see that this is like pretty close to about 250. So just being able to round flexibly is pretty important. When you're multiplying, it's good to round to numbers that are easy to multiply by. So like 18.75, I wouldn't round it to 19 because that's kind of hard to do in your head. Well, I guess we just talked about how to do like 15 times 19. That'd be like your 17 squared minus 4, so 285. So it's pretty close to 285, but let's say you don't want to do that, just want to do something really easy. This is pretty close to like 15 times 20. So that's 3. Let me think about it. Yeah, that's 300. Yeah. 15 times 2 is 30. Add another 0, you get 300. This is pretty close to 300. Okay. 305 divided by 20. When you're rounding with dividing, just make sure that you're rounding your numbers to something where you know that one number goes evenly into the other one, or if it doesn't go evenly, maybe you only get like, a 0.5 or something like that, instead of like a whole number. So anyway, with 305 divided by 21, I would probably just like round these to like 300 divided by 20, because 20 goes into 300 15 times. So this is like about 15. When you're dividing, I think that it kind of tends to be more accurate if you are able to round both of them down or round both of them up by just a little bit. I think if you round one up a little bit and round the other one down a little bit, then like it gets slightly messier. But like you shouldn't worry too much about that. Like just kind of think flexibly when you're doing these things, and just use your senses to kind of think about like what would give you the best approximation. Like rounding both of these to like 320, that's like not going to mess up your answer very much. Anyway.